Carlos Tallard, and I'm participating in the 2014 Challenge Program for Georgia Tech, and I'm here to solve for a Math 2000 problem using this system of equation. I'll be solving it using the Gauss-Jordan elimination method for matrices. So let's get this thing started. To solve for this system of equation, we first write this system of equation in the form of a matrix. To do that, we write down all the coefficients within the matrix. So for this case, the first equation will be just 1, 0, -4, 0, -5, 7. Second equation will just be 2, 1, -6, -1, -7, 20. Third equation will be 0, 1, 2, -1, 0, 6. And the last equation is just 0, 0, 0, 1, 0. So we need to determine whether the system of equation has a unique solution or not, and to do that we must reduce this matrix in the form of row-reduced echelon form. And first step for reducing this in row-reduced echelon form, we look at the first non-zero element in the first row, which in this case is our 1. So our 1 is our first non-zero element, and it's also our pivot for the first column, and we need to have the pivot remaining with everything else above and below it as 0. Since our 2 is not reduced to 0, we must reduce it using row operations. So we set the second row equaling the pivot being multiplied by -2 for row 1, and adding it back to row 2. And this will be set as 1, 0, -4, 0, -5, 7. And this will be 0, 1, 2, -1, 3, and 6. And then everything else remains the same. Alright, so now here we have our first column reduced to 0 with our pivot remaining. So now we move on to the next pivot, which is right here. It's another 1, so we need to reduce everything else back to 0. So our third row has 1 as our non-zero, so we reduce this using our pivot. And we set, so for this we set the third row equal to the pivot being multiplied by -1, so that would just be negative row 2, and adding that back to row 3. So for there, we will have our matrix as 0, 1, 0, -4, 0, -5, 7. Second row, 0, 1, 2, -1, 3, 6. And the third row would just be 0, 0, 0, 0, -3, 0, and everything else 0, 0, 0, 1, 0. So now we have our second column reduced to 0 with our pivot remaining. So we move on to the next pivot of the continuing columns. For this case, it would just be -3. So we have 3 non-zero elements above and below it of our pivot, and we need to reduce that to 0. To shorten things up for this process, we'll just write down the row operations for each row. So for the first row, we'll have to set that equal to the pivot of row 3 being multiplied by -5/3 for row 3, and adding that back to row 1. Then our second row will just be second row being added by the third row of the pivot, and fourth row will be set equal to this pivot row of row 3 being multiplied by -1 by 1/3, positive 1/3, and then back to row 4. And this will be solved for as 1, 0, -4, 0, 0, 7, then it's 0, 1, 2, negative 1, 0, 6, then it's just 0, 0, 0, 0, negative 3, 0, and then the last row would just be 0, 0, 0, 0. Okay, so now we have all our non-zero elements eliminated with our pivot remaining, but since we need to have this in row reduced outcome form, we need to reduce our pivot to positive 1. So we set the third row as negative 1/3 times the third row, and that will just leave us with 1. And by now it is in reduced row echelon form. So now we have reduced it in the final step. Now I'm going to rewrite this back into a system of equation form and have this using the same variables. So this let's see. So this would be just x1 minus 4x3 equaling 7. Then it's x2 plus 2x3 minus x4 equals 6. And x5 equals 0. So now that we have this rewritten, I'm going to write this again, but using the terms of x3 and x4. And the reason why is because our third and fourth column has two free variables for the matrix, which in this case makes our row reduced echelon form not having a unique solution. So I'm just going to rewrite this in terms of x3 and x4. So that will just give us x1 equaling 7 plus 4x3, x2 equaling 6 minus 2x3 plus x4, x3 equaling x3, x4 equaling x4, and x5 equaling 0. So now we have it in terms of x3 and x4. We want to write our answer in a vector equation. So I'm going to set x3 as assign it to as s, and x4 assigning this to t. So I can write this as a parametric equation. And from here, our vector equation for x, vector x, will be constants at x1 7, x2 6, at x3 0, x4 0, and x5 0, plus our parametric s times our coefficient on x3, which is 4 at x1, negative 2, 1, 0, 0, and then our vector for t over x4, which in this case for x1 is 0, 1, 0, 1, 0. So our final answer is this right here, and that's how you solve for the linear system of equations. And oh yeah, and since this just in this form of derivative equation, since there's two free variables, that means that this system of equation has plane, a geometric plane, which in this case, let's see, geometric plane. So in this case, there will be two directions going in these two forms from one single point, going these two directions, and this will just form a geometric plane within the same amount of space. And that's it.